Well, makes sense. The question makes sense. We want to know if we ask this combinatorial definition that a set so that when you hit it by a line you get at most 2 points. When you put the condition that the size is q plus 1, do you get the conics? Or do you get some weird examples? Do you want to know the answer? No? You may not be able to do the homework, so maybe I'll better tell you. Anyway, so Segre came up in 1955. Segre was a Italian geometer. And by the way, there are two Segres, Benjamino and Corrado. Corrado was a classical algebraic geometer. And Benjamino Segre started this new field of finite geometry by publishing this paper in 1955. A beautiful paper. The answer is yes, if Q is odd. So for instance, 5. But the answer is undecided otherwise. Okay? I mean, he doesn't talk about this case. His case is only when Q is odd. He proves that if you give me an object with Q plus 1 points, no 3 on the line, he can show you the equation. Yeah, this is really magic. It's a beautiful proof. And but it still puzzled people because they still did not know about this case. The second case where Q is even is undecided. And I guess what he did is tell his graduate students, hey, tell me something about this. And it took a while, and Lunelli and She, these are Italian mathematicians, found the counterexamples. And they found the example when Q is 16, which is an even number, so we're in this case. He found an example of Q plus 2 points that doesn't arise from an oval. So in particular, you have Q plus 1 points for which you cannot find an equation. Do you want to know what this example is? I mean, I don't know how much time we have. It's very easy to put it up here. So in F16, going back to finite fields, if you want to define a finite field, now this is the one where Q is a prime power. That's the one where it's a little more complicated. You need to find a polynomial of degree 4. It has to be irreducible, and then you adjoin the root. So you could say that F16, for instance, eta is a primitive element, so that F16 would be written as F2 adjoined eta. And for instance, you could take eta to the power 4 equals eta cubed plus 1. This would be a choice. You could choose a different one, but as long as it's irreducible, it's OK. It has to be a primitive, so as long as it's irreducible primitive polynomial, you will be fine. Remember this theorem by Moore, the finite fields of a given order, they are all isomorphic. So whatever you will find, you can do. I just choose this one here, and we're going to define two cubics. So the first one has the equation x cubed, y cubed, z cubed, plus eta cubed xyz. That's a cubic. The second one has x cubed plus y cubed plus z cubed plus eta to the 12th xyz. So to get me, don't get me wrong when I say cubic, I'm writing down an equation. What I mean is the variety, the zero set of this equation. The set of points in the plane that when you substitute, you get 0. Maybe I'll just put a 0 here. Okay? So you have these two cubics. Now what are you going to do? You're going to form this guy, the delta between two sets. If you have two sets, the delta is the symmetric difference. Have you heard that? The symmetric difference. So what that is you take C1, subtract C2, and you unite it with C2, subtract C1. I'll draw a little picture. So if you have two sets, A and B, what you take is you take the stuff that's in one of them, but not in the intersection. And so if you take the symmetric difference of these two cubics, you'll find an object that is that does not arise from a conic. And how do you prove that this is not the same? Yeah, how do these people know that they found something new? Well, I'm not sure how they did that, but I could tell you how I would do it now. So you would consider the regular one, which is the one that's the conic plus a point. I didn't really tell you the whole story, so bear with me. We have a little, didn't tell you what this point is, but if you have a conic in characteristic 2, there's a unique point that kind of wants to be added, and it still has the property that every line intersects in at most 2 points. And so that's how we get to the regular hyperoval. And the Lunelli-Shea hyperoval. And what you could do, and this is not something you want to do by hand, but you can do it nowadays because we have computers. What you want to do is you want to compute the automorphism group of this guy. I didn't really tell you what the automorphism group is. Roughly speaking, it's the symmetries of the plane that preserve the set. And the interesting thing that you will find is that the sizes don't match. This is 16320, and this 144. And then you got to prove that these objects are not isomorphic. It's a computer proof. But it's nowadays, it's maybe the easiest way to see that. And it's, in the meantime, so it's the smallest example you could possibly find. So for 8 or 4, you will not be able to find something that's not the first one. For 16, there was this guy found. And guess what happened in the meantime? You know, this was in the middle of the 60s. They found many, many examples that are not of the first type. So we're in the middle of a huge mathematical mess. We have to sort out and classify the hyperovals for Q of the form 2 to the power something. A huge open problem. So that's maybe a good place to stop for today. What I want to do is hang around here so that you could possibly ask me a question and have you maybe have a look at the homework and work on that. So use me as your resource and ask me questions. Otherwise, give it a shot. Thank you.